Now that we know a little bit about maximums and minimums of functions, it's nice to actually look at more about functions and what the derivatives tell us about the shapes of curves. So we're going to start off with a theorem. There's lots of theorems in calculus to help us understand what's going on. And so this theorem helps us with that. It's called the mean value theorem. And what it says is if f is a differentiable function on AB, a closed interval AB, then there exists a number c in an open interval AB such that f prime of c is equal to f of b minus f of a over b minus a. Or f of b minus f of a is equal to f prime of c times b minus a. Another way to look at it. So what I want to do is just kind of show you what a graph of this would look like, what kind of a visual of an understanding of this. I'm going to draw it in the first quadrant. There's nothing special about the first quadrant. It just makes life a little bit easier. I'm going to have some function here. This function is going to go up and then come back down, go down a bit, and then come back up. Here is A at the one end, and B is at the other end. And then f of b minus f of a over b minus a is a line. It's the secant line. So it just connects up that point there of a f of a with this point here of b f of b. And it has a certain slope. And what this slope of this line is f of b minus f of a over b minus a. Well, what the mean value theorem tells me is that somewhere in this interval, there's a point, at least one point, where the slope of the secant line is the same as the slope of the tangent line. If you think about it, you could actually think about, let's actually copy this. And I'm going to copy it, and I'm going to paste it back in here. And so I have this, and I can now move that line along. And I'm going to move that line along until I find a place where it's a tangent line, because that's what this derivative is a tangent line, and has the same slope. And right there is that point. So at the top there is that point where that happens. And so that point right there is my C. So that's the point where this derivative here, this line here, has the same slope as that tangent line. So that's f prime of C. And notice the two lines are exactly the same. Now, just as a comment, that wasn't the only place. If I move this line around again, I'm going to find that there's another place where the tangent line is going to be the exact same as that secant line slope. And so that's another C, another place where that happens. We'll call the first one C1 and the second one C2. And again, if I were to draw in the tangent line at that point, I would see that the tangent line and that secant line are exactly the same. So this is what the mean value theorem does for us. A couple other things that it does for us is, or another concept of it, is talking about average velocity. Average velocity is S of B minus S of A over B minus A, where S is your position. So it's your change in position over your change in time. By the mean value theorem, there exists a point C in the open interval AB such that the velocity, the instantaneous velocity, is equal to that S of B minus S of A over B minus A. In other words, there's some point in that interval where the instantaneous velocity is equal to the average velocity over the interval. So when a police officer actually pulls you over and says you're speeding, they don't need to know exactly where you're speeding, exactly where you were speeding in that one interval. They just would know that overall, if your average velocity over that interval was more than the speed limit, then somewhere in there, your instantaneous velocity was over that. Another concept about derivatives tell us about functions is what we call the increasing decreasing test. If the derivative f prime is positive on an interval, then f is increasing on that interval. And we've seen this. Let's go back and look just quickly at this graph. You can see this. Here, I'm increasing from A to C1. I'm increasing. And notice my derivative would be positive because my slope of my derivative would be positive. So if the derivative is positive on an interval, then f is increasing on the interval. And if the derivative is negative on the interval, then f is decreasing on that interval. Again, looking at this, if you look at a graph and look to see where it's decreasing, you can see if it's decreasing here, the slope of its derivative, the slope of its tangent line or the derivative would be negative. So that works. What I'd like to do is just prove these to you. I'm not going to prove both because they're very, very, very similar. Let's go ahead and prove the decreasing one. So we're going to go ahead and start off and prove that decreasing one. So you don't see a lot of proofs probably before this, so we're going to do a proof and show you kind of how it works. First off, we need to do some assumptions. So we're going to let x1 and x2 be any number, any numbers, because there's two of them, in an interval with x1 less than x2. So we're going to just kind of assume they have these. Now going back to our theorem, notice at the start of the theorem we say if f prime is less than 0 on that interval. So that's actually an assumption. That's what we're given. That's kind of information we have. So given f prime of x is less than 0, we know, since we have that, we know that if f prime is less than 0, we know that the function is differentiable. We know f is differentiable because we are given that there's a derivative and it's less than 0. So it must be differentiable. And so it must be differentiable on the closed interval x1, x2. So if you remember, that was the assumptions behind the mean value theorem, is that f was differentiable on an interval. So we kind of are going to set up to using that mean value theorem. So by the mean value theorem, there exists a number c between x1 and x2 such that f of x2 minus f of x1 is equal to f prime of c times x2 minus x1. So that's what, again, the mean value theorem gets for us. Now, we know, because we were given that the derivative is negative on this interval, and c is in this interval, then f prime of c is negative also, because we know the derivative was negative. That was an assumption we had. We also know that x2 is bigger than x1. So we know that x2 minus x1 is greater than 0. And again, that was since we assumed that x1 was less than x2. So that means that f of x2 minus f of x1, well, if the derivative is negative and x2 minus x1 is positive, we have a negative times a positive. That means that this is negative. So we know that this is negative. That means that f of x2 must be less than f of x1. Well, if f of x2 is less than f of x1, by definition, f is decreasing. All right. So now let's use that idea. Let's actually go ahead and do an example of this. Find where this function f of x equals x to the fourth plus 5/3 x cubed minus 3x squared plus 4 is increasing and decreasing. So the first thing we need to do is find out what's the derivative doing. So it helps to know the derivative. So let's find the derivative first. So this would be 4x cubed plus 5x squared minus 6x. And we want to basically look at the critical points. So we're going to set this equal to 0 to find those critical points. So set this equal to 0, factor it. This factors as x times 4x minus 3 times x plus 2 equals 0. So we have it equal to 0. We went ahead and factored it. And then we know that when we factor that, that means that x could be 0, x could be 3/4, or x could be -2. So there are our critical points. And now what we want to know is what is the derivative doing at these critical points. So let's go ahead and look at that. So I like to make up a table, well, a number line, I should say. A number line. My number line will contain all of my values, all my critical points. So we had -2, we had 0, and we had positive 3/4. So I put those on my number line in the order they are. And then what I'm going to do is I'm going to look at each of the factors. I have an x factor, I have a 4x minus 3 factor, and I have an x plus 2 factor. Well, the x was 0 at 0. Below 0, the x will be negative. Above 0, the x will be positive. 4x minus 3 was 0 at 3/4. If you take numbers less than 3/4, like 0, you're going to get a negative number. So if all the time less than 3/4, you're going to get negative numbers. Bigger than 3/4, you're going to get a positive number. X plus 2 was 0 at -2. If you take a number less than that, you're going to get a negative number. If you take a number bigger than that, you're going to get a positive number. So looking at this, we're going to multiply these all together. We're looking at what the derivative is doing. So we're going to take negative times a negative times a negative is a negative. Positive times a negative times a negative is a positive. Positive times a positive is a negative. And positive, positive, positive is positive. So this tells me that the derivative is negative, less than -2, and from 0 to 3/4. And the derivative is positive between -2 and 0, and 3/4 to infinity. So that tells me that f is increasing wherever the derivative is positive. So f is increasing from -2 to 0, and also from 3/4 to infinity. F is decreasing wherever the derivative is negative. So f is decreasing from -infinity up to -2, and then again also from 0 to 3/4. This actually helps us from this idea, by the way. I can now see the fact that if I'm increasing from -2 to 0, then I'm going up, and then I'm going to start going down again. That must mean something special is happening at x equals 0. And what we can look at is we can see whether or not it's a maximum or minimum. And that gets us into something called the first derivative test. The first derivative test says, suppose that c is a critical number of a continuous function. Then f prime changes from positive to negative at c. Then f has a local max at c. So if f prime is changing from positive to negative at c, then that means we have a maximum, local maximum there. If f prime changes from negative to positive at c, then f has a local min at that point. And if f prime doesn't change signs at c, then f has neither local max or local min. So going back to that, that's for the find the local maximum of the min for the function in example 1. So remember our function in example 1 was f of x equals x to the 4th plus 5/3 x cubed plus 3x squared plus 4. I'm going to write that down again. And we happen to know, we're going to go back, I'm going to draw down the number line I had of what the derivative was doing. So we remember we had critical points of -2, we had critical points of 0, we had critical point of 3/4. So when we were less than -2, the derivative was negative. When we were between -2 and 0, the derivative was positive. When we were between 0 and 3/4, the derivative was negative. And bigger than 3/4, the derivative was positive. So we have all that. So now we can see that as we went negative to positive, that means that x equals -2, there's a local min. So there's a local min at x equals -2 because we were decreasing and then increasing. So you went down and then you came back up. So it must be a local min because you came down and back up. That happens again at 3/4. We came down and then back up because we went from negative infinity, we went negative to positive. So it also is at x equals 3/4. Now those aren't the min value, that's just the location of them. We have a local max. We were increasing, so we're going up from -2 to 0, and then at 0, we turn and we head back down again. So that must mean at 0, we have a local max. Again, that isn't the local max, it's just the location of it. Now, if I want to actually find the local min, then all I got to do is find out what f of -2 is equal to. So I just put -2 into my function and find out what value I get. And when I plug it in, I find that it's equal to -16/3. I also had a local min at at 3/4. So my function, my local min is f of 3/4. So I put 3/4 into my function and I find out I get 853 over 256. I have a local max. My local max occurs at 0. So I just need to do f of 0. F of 0 happens to be 4. So my local max is 4. I have local min values of -16/3 and 853 over 256.